What was the Earth like when it saw the birth of life? A question that has intrigued science for centuries. Today, most scientists insist that it was born from a simple chemical reaction, which chaotically transformed non-living matter into the first living cell. Nevertheless, this explanation is insufficient in the absence of concrete evidence, even for its most ardent supporters. Today, every corner of the Earth is full of life. From the poles to the equator, from deep caves to mountain ranges, from tropical forests to volcanoes, at least primitive organisms can be found everywhere. Animals, plants, fungi, and bacteria in search of living space have adapted to the harshest conditions. However, scientists believe that for most of its history, the Earth has looked like a rather inhospitable place. When life first appeared on Earth about 3.8 billion years ago, the planet looked very different from what we know today. At that time, the Earth's surface was mostly water, with small archipelagos and undeveloped land masses. The atmosphere was also very different from today's, with a high proportion of gases such as methane, ammonia, and carbon dioxide. These gases were produced by massive volcanic eruptions and chemical reactions in the primitive oceans. There was also very little oxygen in the atmosphere, because photosynthetic organisms capable of producing oxygen had not yet appeared. Dear traveler, welcome. Today we are going on an incredible journey through time to the origins of life. But before leaving for a new adventure, think about liking the video and subscribing to the channel so you don't miss anything. Thank you, and have a nice trip. Scientists use a variety of methods to study the environmental conditions on Earth when life first appeared, including the study of rocks and fossils. The most direct way to learn about the structure of the Earth's crust and its history is to study rocks directly, observing their composition and position in the crust. Thus, scientists can study rocks and fossils to determine the environmental conditions that existed at the time, 3.8 billion years ago. The rocks have different origins. How they form can often be told by the rocks themselves, if they are properly compared to rocks that are forming before our eyes today, and whose origin is clear. For example, the chemical composition of the rocks can indicate the levels of oxygen, carbon dioxide, and greenhouse gases in the atmosphere at that time. Also, if the rock contains corals or shells, similar to those living in the sea today, it is concluded that the rock was formed on the seafloor. If the leaves and trunks of plants are imprinted on the layers of clay or sandstone, we must deduce that these rocks have accumulated somewhere on land, perhaps at the bottom of a lake, into which plants have fallen. Fossils can also be used to judge the depths of the ancient sea. For example, corals live in shallow marine coastal environments. Therefore, coral limestones indicate a shallow sea. However, the paleontological method has significant limitations in cases where the rocks contain new fossil, organic remains, or where these remains are not characteristic. Continental deposits, such as those in river valleys and lakes, contain far fewer fossils than marine rocks, making age determination much more difficult and less accurate. Scientists can analyze isotopes in rocks, fossils, and sediments to determine environmental conditions. This method only appeared with the discovery of radioactivity in the early 20th century. It is based on the natural transformations of radioactive elements. These transformations occur at a constant rate and can therefore be used as a natural hourglass. For example, the amount of carbon-13 isotope in fossils can give indications about the type of vegetation that existed at that time. The use of radioactive methods to determine the absolute age of minerals has further developed our understanding of the Earth's history, although these methods also have limitations. Scientists can use computer models to simulate and analyze the environmental conditions that dominated the Earth at the time of the appearance of life. These models can also be used to test different hypotheses about the processes that led to the emergence of life. In computer modeling, a computer uses algorithms and data to create models that simulate the behaviors of living things based on their characteristics and environmental conditions. In addition, these models can take into account factors such as the tilt of the Earth, the distance between the Earth and the Sun, greenhouse gas levels, and other elements that affect climate. Scientists can study present-day life to better understand the environmental conditions that supported the emergence of life. By studying current life forms and the environments in which they thrive, we can learn more about the criteria for the ideal habitat for life and understand how life has evolved to adapt and survive in different environments. For example, studying bacteria that live in extreme environments, such as hydrothermal springs, can provide insights into the environmental conditions that allowed life to emerge on Earth. It can also help us better understand how living things can be affected by environmental changes and how we can protect them. Questions about the origin of life are of interest to humans who wish to interpret the world around them, understand, and determine their place in the universe. The origin of life is one of the three most important mysteries, along with the origin of our universe and the origin of man on Earth. Centuries of research and attempts to solve these problems have given rise to different concepts of the origin of life. The first traces of theory on the spontaneous origin of life born in Babylon, Egypt, and China. It is based on the concept that under the influence of natural factors, the living can arise from the inanimate, and the organic can come from the inorganic. It goes back to the Greek philosophers Empedocles and Aristotle. Certain particles of matter contain some kind of active principle that, under certain conditions, can create a living organism. Aristotle believed that the active principle could be found in a fertilized egg, sunlight, and rotting meat. For the Greek philosopher Democritus, the beginning of life occurred in wet places, such as ponds or swamps, for Thales in water, for Anaxagoras in the air, Based on information about animals from the soldiers of Alexander the Great and merchant travelers, Aristotle formed the idea of a progressive and continuous development of living from the inanimate, and created the idea of the scale of nature. According to this conception, all living and inanimate beings occupy a specific position in the scale of complexity and perfection. At the top of this ladder is God, followed by angels, humans, animals, plants, and finally minerals. Each step of the ladder is higher than the previous one, in terms of complexity and perfection. The followers of this concept did not doubt the spontaneous generation of frogs, mice, and other small animals. The Greek philosopher Plato spoke of the spontaneous generation of living beings from the decaying earth. The idea of spontaneous generation spread in the Middle Ages and Renaissance, when the possibility of spontaneous generation not only of simple creatures, but also of more complex organisms. The Belgian scientist Jean-Baptiste van Helmont is best known for his concept of spontaneous generation. He proposed a recipe for obtaining mice from wheat and dirty laundry. Francis Bacon also believed that the decomposition of existing things was considered the starting point for the creation of new things. While in the 17th century, the ideas of spontaneous generation of life were supported by Galileo, Descartes, Harvey, and Hegel, the Florentine naturalist Francesco Redi conducted a series of experiments with insects to demonstrate that the theory of spontaneous generation was false, and that insects did not arise spontaneously from decaying meat, as was then believed. By putting meat in a closed pot, Redi showed that fly larvae do not spontaneously generate in rotting meat. The proponents of the spontaneous generation theory did not give up, however. They argued that the spontaneous generation of larvae did not occur for the sole reason that air did not enter the closed pot. Thus, Redi placed meat in several jars, sealing some, while others were left open. He observed that the sealed jars did not develop larvae, while the open jars contained larvae. This showed that the larvae did not come from the meat itself, but rather from eggs laid by flies that had landed on the meat. In the 17th century, the German mathematician and philosopher Leibniz continued to defend the theory of spontaneous generation of life. He and his followers argued that there is a special life force in living organisms. According to this idea, the life force is an active force that is responsible for the organization and regulation of vital functions. It is present everywhere. It is enough to inspire it, and the inanimate then becomes alive. The invention of the microscope opened the world of microorganisms to scientists. Observations have shown that in a hermetically sealed bottle containing meat broth or a hay infusion, microorganisms are detected after a certain time. But once this piece of meat is boiled for an hour and the neck is closed, nothing appears in the sealed bottle. Vitalists have suggested that prolonged boiling kills the life force that cannot enter the sealed bottle. With the advent of Darwin's Origin of Species, the question once again arose as to how life on Earth came to be. The French Academy of Sciences launched a competition in 1859 to try to elucidate the question of spontaneous generation in a new way. It awarded a special prize in 1862 to the famous French scientist Louis Pasteur for his work in this area. Pasteur conducted an experiment that rivaled Reddy's famous simplicity experiment. He boiled various nutrient media in a flask in which microorganisms could grow. Prolonged boiling in the flask killed not only the microorganisms, but also their spores. Aware of the vitalist's assertion that the mythical life force could not enter a sealed flask, Pasteur attached an S-shaped tube with an open end. The spores of microorganisms settled on the surface of a thin curved tube that could not penetrate the nutrient medium. The well-boiled nutrient medium then remained sterile, so spontaneous generation of microorganisms was not observed, although access to air and, with it, the famous life force was provided. Thus, for the moment, it has only been proven that any organism can only appear from another living organism. Panspermia is a theory according to which life on Earth could have appeared thanks to microorganisms transported by objects, such as meteorites or comets. According to this theory, these microorganisms would have traveled through space until they reached our planet, where they would have then prospered and evolved to give birth to the life we know today. Nevertheless, this theory offers no mechanism to explain the primary origin of life and transfers the problem to another place in the universe. Some scientists believe that the atmospheres of celestial bodies, as well as rotating cosmic nebulae, could be considered as age-old repositories of animate form, as eternal plantations of organic seeds. From then on, life could dissipate in the form of these germs in the universe. In 1865, the German physician Richter put forward the hypothesis of cosmozoa, or cosmic germs, according to which life is eternal, and the germs that populate the world space can be transferred from one planet to another. This hypothesis has been supported by many scientists. At the beginning of our century, the Swedish chemist Svante Arrhenius had the idea of radiopanspermia. He described how particles of matter, dust particles, and living spores of microorganisms leave planets inhabited by other creatures in space. Arrhenius proposed that these organisms could be protected from the rigors of space by mineral particles in which they would be trapped, forming spores resistant to radiation and extreme temperatures. Once on Earth, these spores could awaken and grow under favorable conditions. Another theory, known under the concept of physico-chemical processes, is based on the hypothesis of the gradual emergence of life on Earth from inorganic substances through long-term, non-biological molecular evolution. Several scientists contributed to the development of this theory, including the Russian biochemist Alexander Oparin, who published a book entitled The Origin of Life in 1924, in which he proposed a thesis that life emerged from simple organic molecules in a primitive environment on Earth. In addition, American scientists Stanley Miller and Harold Urey conducted a famous experiment in 1953, known as the Miller-Urey experiment, in which they demonstrated that simple organic molecules such as amino acids could be produced from inorganic gases under the effect of electrical discharges, thus simulating the presumed conditions of the early Earth. At the beginning of its history, the Earth was a hot planet. Due to its rotation, and with the progressive decrease of its temperature, the atoms of heavy elements migrated towards the core, while the atoms of light elements, hydrogen, carbon, oxygen, nitrogen, were concentrated in the superficial layers, constituting the bodies of living organisms. With the continuous cooling, chemical compounds such as water, methane, carbon dioxide, ammonia, hydrogen cyanide, as well as molecular hydrogen, oxygen, and nitrogen appear. The physico-chemical properties of water, such as its high dipole moment, viscosity, and thermal capacity, as well as those of carbon, such as its difficulty in forming oxides and its ability to reduce and form linear compounds, have made them the founding elements of life. The primary atmosphere of the Earth was different from the current atmosphere. It was not of an oxidizing character, as it is the case today, but of a reducing character. Moreover, it was rich in inert gases, helium, neon, argon. This original atmosphere has evolved to our current atmosphere, composed of 20% oxygen, one of the most chemically active gases. This concentration of oxygen is a product of the development of life on Earth over the billions of years of its evolution. A further drop in temperature led to the transition of a number of gaseous compounds into liquid and solid states, and the formation of the Earth's crust. As the Earth's surface temperature dropped below 100 degrees Celsius, or 212 degrees Fahrenheit, water vapor thickened. Long showers accompanied by frequent thunderstorms led to the formation of large reservoirs of water. The first oceans were formed. As a result of active volcanic activity, a large amount of the hot mass was brought to the surface of the Earth's inner layers, including carbides, which are compounds of metals with carbon. The interaction of carbides with water caused the creation of hydrocarbons. Warm rainwater, as a good solvent, contained dissolved hydrocarbons, gases such as ammonia, carbon dioxide, and hydrocyanic acid, as well as salts and other compounds that could enter into chemical reactions. The chemical combination between oxygen atoms, carbon atoms, and nitrogen atoms allowed the reaction of nitrogenous bases, which are organic molecules. Thus, the simplest organic compounds gradually accumulated on the surface of the young planet Earth in large quantities. Estimates show that about 1,016 kilograms of organic molecules could have been formed on the surface of the Earth by volcanic activity alone. This is only a few orders of magnitude less than the mass of the current biosphere. A spectroscopic study of stellar atmospheres has shown the presence in the so-called cold stars, of which the Sun is a part, of an important part of the carbon associated with hydrogen, and has thus revealed the formation of the most elementary hydrocarbon, methane. It is possible that along with this organic chemical compound, these stars also contain more complex hydrocarbon compounds. It is certain that these compounds are formed abiogenically, that is, from non-living matter. Hydrocarbons also exist in parts of the universe where the temperature is near absolute zero. Undoubtedly, methane is present in the atmosphere of Jupiter, Saturn, Uranus, Neptune, and other planets in large quantities. In addition, the presence of quite complex hydrocarbons has been noted in a number of meteorites, in which no trace of living beings could be established. Finally, the synthesis of hydrocarbons can be achieved experimentally in the presence of a set of certain physical and chemical conditions, such as temperature, pressure, electric field, etc. Thus, the abiogenic formation of organic compounds such as hydrocarbons is not only possible, but also widespread in the universe. It is quite logical to assume that the Earth in the early stages of its existence already had a certain amount of hydrocarbons. The second stage of biogenesis was characterized by the appearance of more complex organic compounds, including proteins, in the waters of the primary ocean. Due to the high temperature, lightning discharges, and increased ultraviolet radiation, the relatively simple molecules of organic compounds interact with other substances to form more complex substances, such as carbohydrates, fats, amino acids, proteins, and nucleic acids. The possibility of such a synthesis was proved by the experiments of Alexander Butlerov, who in the middle of the 19th century obtained carbohydrates from formaldehyde. In addition, an experiment was conducted in 1953 by Stanley Miller and Harold Urey at the University of Chicago, whose objective was to reproduce the conditions of the primitive Earth and try to understand how the first organic compounds could be formed. To this end, they created a primitive atmosphere in the laboratory by mixing water with gases such as ammonia, methane, water vapor, and hydrogen, with a temperature between 70 degrees Celsius and 80 degrees Celsius, or between 158 degrees Fahrenheit and 176 degrees Fahrenheit, and a pressure of several atmospheres under the influence of electric discharges, with a voltage of 60,000 volts and ultraviolet rays. After a few days, Miller and Urey found that amino acids such as glycine, alanine, aspartic acid, and glutamic acid, which are the basic material of proteins, as well as other organic acids, were produced in their experiment. The experiment gave rise to the concept of the primordial soup of life, which later gained popularity. Thus, the conditions of the Earth's primary atmosphere were modeled, in which amino acids could form, and subsequently, primary proteins from their polymerization. This discovery was considered a key step in understanding the origin of life on Earth. Later, other experiments in this direction proved promising, especially with the use of other ratios of initial gases and types of energy to create more complex molecules from simple molecules by polymerization, reaction of proteins, lipids, nucleic acids, and their derivatives. Later, scientists proved the possibility of synthesizing other complex biochemical compounds under laboratory conditions, including protein molecules such as insulin with nucleotide nitrogen bases. Thus, laboratory experiments have confirmed the possibility of formation of protein molecules in the absence of life, which is particularly important. From a certain stage of the chemical evolution process on Earth, oxygen began to play an active role. It was able to accumulate in the Earth's atmosphere as a result of the decomposition of water and water vapor under the action of the sun's ultraviolet rays. It took at least 1 to 1.2 billion years for the transformation of the reduced atmosphere of the primary Earth into an oxidized atmosphere. With the accumulation of oxygen in the atmosphere, the reduced compounds began to oxidize. Thus, during the oxidation of methane, methyl alcohol, formaldehyde, formic acid, etc. are formed. The resulting compounds were not destroyed because of their volatility. Leaving the upper layers of the Earth's crust, these compounds were transported to a cold and humid atmosphere, which protected them from destruction. Consequently, these substances, along with rain, fell into the seas, oceans, and other watersheds. Accumulating in these environments, these compounds again entered into reactions to give more complex substances, such as amino acids. For certain solutes to interact with each other, a sufficient concentration of them in the solution is necessary. It is also important that the more complex organic compounds are more resistant to the harmful effects of ultraviolet radiation than simple compounds. An analysis of possible estimates of the amount of organic matter that accumulated inorganically on the early Earth is impressive. According to some calculations, several kilograms of organic compounds were formed on every square centimeter of the Earth's surface over 1 billion years. If they were all dissolved in the world's oceans, the concentration of the solution would be about 1%. This is a fairly concentrated broth. In such a broth, the process of forming more complex organic molecules could successfully develop. Thus, the waters of the primary ocean became progressively saturated with a variety of organic substances, forming a primordial soup. It should be noted that the activity of subterranean volcanoes contributed greatly to the saturation of such an organic broth. The concentration of organic substances increased in the waters of the primitive oceans. They mixed, interacted, and combined into small structures separated from the solution. Such structures can be easily obtained artificially by mixing solutions of different proteins, such as gelatin and albumin. The Russian scientist Alexander Oparin named the isolated organic structures in solution coacervates. Due to the interaction of opposite electric charges, an aggregation of colloidal organic molecules in suspension occurs. They spontaneously gather in aqueous solution to form spherical structures of high density. Studies have shown that coacervates have a rather complex organization and possess a number of properties that bring them closer to the simplest living systems. For example, they are able to absorb various substances from the environment that interact with the compounds in the drop itself and increase in size. These processes resemble to some extent the primary form of assimilation. At the same time, processes of decomposition and release of dissociation products can occur in the coacervates. The relationship between these processes and different coacervates is not the same. Thus, dynamically separated, more stable structures with a predominance of synthetic activity are distinguished. Nevertheless, all this still does not allow to attribute coacervates to living systems because they do not have the capacity to self-reproduce and self-regulate the synthesis of organic substances. Membranes could appear during the formation of coacervates, which could then explain how biological membranes came into being. The formation of a membrane structure is considered the most difficult step in the chemical evolution of life. A real living being in the form of a cell, even the most primitive, could not take shape before the appearance of a membrane structure. Biological membranes are aggregates of proteins and lipids capable of separating substances from the environment and enhancing the envelopment of molecules. The increase in the concentration of organic substances in coacervates increases the possibility of interaction between molecules and, consequently, the complexification of organic compounds. In addition to coacervates, the primitive soup accumulates polynucleotides, polypeptides, and various catalysts, without which the formation of the capacity for self-reproduction and metabolism is impossible. The catalysts could also be inorganic substances. Thus, the British scientist John Bernal once hypothesized that the most favorable conditions for the emergence of life were found in small, calm, warm lagoons with a large amount of silt and clay turbidity. In such an environment, the polymerization of amino acids takes place very quickly, without the need for heating, because the mud particles act as catalysts. The main problem of the theory of the origin of life is to explain the emergence of structural protein synthesis. Life did not arise when even very complex organic compounds like DNA molecules were formed, but when the replication mechanism started to work. Therefore, the completion of the biogenesis process is associated with the emergence in more resistant coacervates of the ability to self-replicate constituent parts, with the transition to the synthesis of structural proteins, characteristic of living organisms. During pre-biological selection, these coacervates had the greatest chance of survival, since the capacity for metabolism was combined with the capacity for self-reproduction. The transition to structural protein synthesis was the greatest qualitative leap in the evolution of matter. Nevertheless, the mechanism of this transition is not yet clear. The main difficulty here is that the enzymatic proteins are needed to duplicate nucleic acids, and nucleic acids are needed to create proteins. How do we break this closed chain? In other words, we need to explain how, during pre-biological selection, the self-replicating abilities of polynucleotides combine with the catalytic activity of polypeptides under conditions of spatio-temporal separation of the initial and final reaction products. There are various hypotheses about this, but all are somewhat incomplete. However, at present, the most promising hypotheses are based on the principles of self-organization and synergy theory, and on the concept of hyperspaces, i.e., systems that connect self-replicating or autocatalytic units to each other by cyclic binding. In such systems, the product of the reaction is also its initial catalyst or reactant. Therefore, the phenomenon of self-reproduction appears, which initially could not be an exact copy of the original organic formation at all. The very existence of viruses and phages, which are apparently fragments of pre-biological evolutionary forms, testifies to the difficulties in the formation of self-reproduction. Subsequently, pre-biological selection of coacervates apparently proceeded in several directions. First, in the direction of developing the ability to accumulate special protein-like polymers responsible for accelerating chemical reactions. As a result, the structure of nucleic acids has evolved towards the predominant multiplication of systems in which nucleic acid duplication has been achieved with the participation of enzymes. On this way, a cyclic metabolism characteristic of living beings is established. Secondly, in the system of coacervities, the selection of the nucleic acids themselves has taken place according to the most suitable combination of the nucleotide sequence. As a result, genes are formed. Self-replicating systems with an established stable sequence of nucleotides in the DNA can already be called living systems. There are still many uncertainties about the question of the origin of life. Its final solution still seems far away. For example, it is not known why all protein compounds that make up living matter have only left-handed symmetry, and what mechanisms of pre-biological evolution could lead to this. By examining the main features of the Earth's development, it becomes clear that the path of its evolution was decisively determined both by the Earth's position in the solar system, by the Sun's luminosity, and by its mass and chemical composition. Thus, if our Sun belonged to the type of variable stars, then the Earth would experience extreme temperature fluctuations, oscillating between unbearably hot and cold temperatures. If the mass of the Sun were significantly larger, then it would have exploded after a few tens or hundreds of millions of years after its formation, and turned into a neutron star, or even a black hole. The fact that the Sun is a quiet star with a medium stellar mass, belonging to the dwarf stars of the G2 spectral class, is a determining factor for the appearance and evolution of life on a planet like ours. In addition, it is a stable star that changes its brightness slightly over several billion years. This last characteristic is particularly important because during the last 4 billion years, it has allowed terrestrial life to follow a long evolutionary path from the birth of simple and primitive life to its most complex forms. The distance of the Earth from the Sun has proven to be optimal, since if they were closer to each other, the heat on Earth would be excessive, which could lead to an irreversible greenhouse effect as on Venus. And if this distance were greater, the Earth would be frozen and could undergo a stable glaciation, becoming an ice-covered planet. Another important element is that the Earth has a massive satellite like the Moon. It has been reported in a study that the presence of the Moon in a close orbit to the Earth has considerably accelerated the tectonic development of the Earth. If our planet had not had a massive satellite, then it would probably have rotated slowly in the opposite direction, like Venus, delaying its tectonic development by 2.5 to 3 billion years. In this scenario, the Earth would have conditions similar to the late Archean, i.e., with a dense carbon dioxide atmosphere and high temperatures, and instead of highly organized life, the Earth would be inhabited only by primitive bacteria or single-celled prokaryotes. Observing the close interaction of the Earth with the Sun and the Moon, one is amazed at the optimality and equilibrium of this system that has been so successful in creating on our planet very comfortable conditions for the emergence and development of highly structured organisms. The Earth is able to contain a moderately dense atmosphere on its surface, as well as by its exceptionally perfect chemical composition. Indeed, even relatively small deviations from the initial concentrations in terrestrial matter of elements and compounds, such as Fe, CO2, H2O, N2, etc., could have irreversible and catastrophic consequences for life. In particular, if there was less water in the Earth's primary matter, then carbon dioxide would be absorbed with less intensity and would start to accumulate in the Earth's atmosphere. Thus, even in the Archean, an irreversible greenhouse effect could have occurred, and our Earth would have turned into a hot planet like Venus. And if there had been significantly more water or less free iron, then the Earth would have become an ocean planet. Moreover, if the amount of nitrogen on Earth had been less, the planet could have been completely covered with snow and very cold by the beginning of the Proterozoic. Nevertheless, with a greater amount of free iron in the primary terrestrial material of the modern atmosphere, as in the Proterozoic, free oxygen could not have accumulated, and consequently, the animal kingdom could not have arisen on Earth. On the contrary, if the initial concentration of iron had been lower, this would have led to an abundant release of endogenous oxygen, already at that time or even earlier, which would have caused the burning of all life on Earth in such an atmosphere. In addition, the process of oxygen outgassing would have led to a strong greenhouse effect, after which the Earth would have also turned into a hot planet like Venus. Nobody knows exactly when the first living cell appeared. The age of the first traces of life is about 3.5 billion years. They are remains of bacteria found in the ancient deposits of the Earth's crust. Therefore, the age of life on our planet is about 3.5 billion years. The earliest period of life development, the Precambrian, is an incredibly long time, 4 billion years. We have already talked about the conditions in which the first living organisms lived. Their food was organic matter from the primitive soup of the surrounding ocean. However, little by little, over millions of years, this environment became poorer and poorer in organic matter, and eventually, the supply of nutrients was exhausted. The first inhabitants of our planet were heterotrophic beings that fed on organic substances dissolved in the primordial ocean. The progressive development of primary living organisms subsequently provided the opportunity for a huge leap forward, including the emergence of autotrophic beings that use solar energy to synthesize organic compounds from the simplest inorganic compounds. Of course, a compound as complex as chlorophyll did not appear immediately. Initially, simpler pigments appeared, which mainly contributed to the absorption of organic substances. Gradually, in the primordial ocean, the organic substances that had accumulated abiogenetically began to be gradually depleted. The appearance of autotrophic organisms, mainly green plants, ensured the continued synthesis of organic substances, and consequently, the existence and further development of life. The development of life almost came to a halt, but evolution managed to find a way out. The first organisms to appear, bacteria, were able to transform inorganic substances into organic ones with the help of sunlight. To build their organisms, all living beings need hydrogen in particular. Green plants obtain it by breaking down the water molecule and releasing oxygen. But bacteria were not yet able to do this. They could not break down water because it is not so easy to separate the bond between the hydrogen and oxygen atoms. but they manage to break down hydrogen sulfide, which is much easier. In this case, it is not oxygen, but sulfur that is released. Thus, a layer of sulfur can be found on the surface of some swamps. But the amount of hydrogen sulfide on Earth was rather limited. A new crisis in the development of life occurred. The blue-green algae found a way out. They learned to break down the water molecule, a process that is 7 times more difficult than breaking down hydrogen sulfide. You could say that these algae have accomplished a real feat. This happened 2,300,000,000 years ago. From then on, as a byproduct, oxygen began to be released into the atmosphere, which at that time posed a serious threat to life. Therefore, a new spontaneous generation of life on Earth became impossible. In fact, the oxygen content reached 1% of its current level, and living organisms were faced with a new problem: how to cope with the increasing amount of this aggressive substance. Once again, evolution managed to overcome this difficult test. Thus, the first organism to inhale oxygen appeared on Earth. Until now, living organisms lived in the ocean, hiding in the water column from the sun's ultraviolet rays, which are harmful to all living things. Now, thanks to oxygen, a layer of ozone has appeared in the upper atmosphere, attenuating the radiation. Under the protection of ozone, life was able to settle on the Earth's surface. In the Precambrian, nature made a number of remarkable inventions. Cells received a nucleus. At about the same time, sexual reproduction appeared, greatly accelerating the pace of evolution. The first multicellular creatures appeared. At the end of the Precambrian, the seas were inhabited by a variety of animals: jellyfish, flatworms, sponges, and polyps. All were soft-bodied, lacking skeletons. The appearance of a shell framework in animals marked the beginning of a new geological era. Having emerged, life began to develop at an accelerated rate. Thus, the development of primary protobionts to aerobic forms took about 3 billion years, while about 500 million years passed since the emergence of land plants and animals. Birds and mammals evolved from the first land vertebrates in 100 million years. Primates evolved in 12 to 15 million years, and it took about 3 million years for the formation of modern man. The most important factor ensuring the very existence of life on Earth is first and foremost the process of degassing of the planet, which was the origin of the appearance of the oceans and the dense atmosphere. Without this process, life as we know it would not have been possible on Earth. The degassing of the Earth that began during the Archean period led to the formation of a relatively dense atmosphere of carbon dioxide and nitrogen. During this time, volcanoes, magma rocks, and the first shallow sea basins appeared, which in the middle of the Archean merged into a single, but still shallow ocean. During the Archean, thanks to a high atmospheric pressure between 0.5 and 1.1 atmospheres, the average temperatures of the oceanic waters, as well as of the surface layers of the troposphere, reached between 30 and 50 degrees Celsius, or between 86 degrees Fahrenheit and 122 degrees Fahrenheit. The carbon dioxide composition of the atmosphere has also resulted in acidic ocean waters with a pH between 6.3 and 7.7. Although the first stage in the development of terrestrial life is not yet entirely clear, stromatolite formations date back 3.6 to 3.5 billion years. For example, the stromatolites of the Barberton Belt in eastern South Africa have a siliceous composition and are thin, short layers present among chert beds in the volcanic rocks of the Greenstone Belt. By the middle of the Archean, terrestrial life was already characterized by a somewhat greater diversity, and probably by the complete dominance of thermophilic, prokaryotic forms, mainly chalcophilic and siderophilic archaea. Most probably, these primitive life forms were then fed by chemogenic reactions, i.e., chemical reactions that produce heat, of the type currently used by thermophilic bacteria in the hot hydrotherms of the mid-ocean ridges, as well as other anaerobic chemogenic reactions. Because the concentration of free iron was low in the Archean convective mantle, above the zones of terrestrial material differentiation, oxygen was probably present in small amounts in the Archean atmosphere. Over time, oxygen was released due to the photodisassociation of water vapor by the sun's harsh radiation and the vital activity of cyanobacteria, which had already appeared by this time, since stromatolites are found in the Archean. In the middle of the Archean, about 3.1 billion years ago, the mass of water in the Earth's hydrosphere increased so that individual marine basins began to merge with each other into a single global ocean. The ocean surface then covered the ridges of the mid-ocean ridges. As a result, the hydration processes of the oceanic crust became somewhat more active. This caused the increase of calcium carbonate input to the oceanic crust. This led to a noticeable increase in carbonate deposits at the end of the Archean, such as marbles and calcifers in eastern Russia, as well as stromatolite deposits in the Greenstone belts, although their share in the volcanogenic formations of these belts still remained insignificant. The second radical geological and biological stage was associated with the separation of the Earth's core and a sharp decrease in the Earth's tectonic activity at the turn of the Archean and Proterozoic, about 2.5 billion years ago. It was at this time that the serpentinite layer first appeared in the oceanic crust, which is the main reservoir of bound water in the Earth's crust and is constantly renewed. The hydration of ultra-basic rocks is accompanied by the absorption of carbon dioxide and its fixation in carbonates. This should explain the relatively rapid removal of carbon dioxide from the atmosphere and the drop in total atmospheric pressure from 6 atmospheres to about 1 atmosphere, and average temperatures from 50 degrees Celsius or 122 degrees Fahrenheit to about 7 in the early Proterozoic. This abrupt cooling of the climate led to the emergence about 2.5 billion years ago of the first ice age in Earth's history. However, it must be taken into account that during the late Archean and early Proterozoic, a large amount of raw material containing a high concentration of metallic iron rose into the Earth's mantle from the central core. As a result, the mass of iron supplied to the oceans through the rift zones on the Earth far exceeded the possibility of oxygen formation in the biosphere. It follows, therefore, that in the early Proterozoic atmosphere, there was extremely little oxygen, probably no more than 0.001% of the present content, and even lower during the massive deposition of jaspilites. But unlike the Archean atmosphere, it already contained only a few millibars of carbon dioxide. This suggests that it was during the times of massive deposition of iron ore formations that iron-forming bacteria probably also appeared, consuming oxygen through the reduction of iron to magnetite phase. It is possible that oxygen deficiency could also activate symbiotic processes in the life of the simplest bacteria, leading to the formation of mitochondria and cell nuclei, which then form the basis for the emergence of eukaryotic life forms. Thus, the Earth's atmosphere, at the beginning of the Proterozoic, about 2.5 to 2 billion years ago, was composed primarily of nitrogen, with small amounts of water vapor, argon, and carbon dioxide. Such drastic changes in habitat conditions could only affect the biota of that time. The thermophilic prokaryote community had to give way to more bacteria and microalgae. Another revolutionary change was associated with these events in the biota of the oceans. By the beginning of the early Proterozoic, photosynthetic microorganisms, the blue-green algae, were widespread, and there was a sharp increase in the abundance of stromatolites in geologic history, which corresponds to the era of mass depositional iron ore formations. In the early Proterozoic, after the serpentinite layer of the oceanic crust appeared, the concentration of carbon dioxide in the atmosphere dropped sharply, resulting in the formation of huge masses of calcium and magnesium carbonate. This should have led to the formation of the most powerful sequences of chemogenic and organogenic dolomites. Indeed, carbonate strata 500 to 1,700 meters thick, or 1,600 to 5,600 feet thick, of the Wayland, Michigan series in North America, and the Transvaal series in South Africa, with associated stromatolites, were deposited at this time. During the Middle Proterozoic, i.e., after the end of the era of massive deposition of iron ore formations, 2 to 1.8 billion years ago, some increase in the partial pressure of oxygen occurred in the Earth's atmosphere. As a result, many species of unicellular bacteria and algae develop rapidly, and probably the first eukaryotic unicellular organisms appear, most likely formed as a result of endosymbiosis of prokaryotic bacteria. The metabolism of eukaryotic microorganisms was already associated with the absorption of small amounts of oxygen, so that they could propagate widely only after an increase in the partial pressure of this gas in the Earth's atmosphere to a certain level. Therefore, at the turn of the Middle and Upper Proterozoic, the new profound restructuring of the trophic structure of the ocean began, associated with a rapid spread of eukaryotic organisms and phytoplankton. It is possible that in the Middle Proterozoic, the Earth was also colonized by a bacterial flora, which in particular can be evidenced by the red-colored weathering crusts that first appeared at this time. In this respect, it should be noted that the binding of nitrogen in the organic matter of these bacteria and the subsequent burial of nitrogenous compounds in the sedimentary layers should have resulted in a gradual decrease in the total pressure of the Earth's atmosphere. The consequence of this decrease in atmospheric pressure was the progressive cooling of the climate at the end of the Proterozoic. As a consequence, and also due to the drift of part of the Gondwanaland and Laurasia continents towards high latitudes, a new ice age was observed at the beginning of the Middle Paleozoic. The transition of the atmosphere at the turn of the Archean and Proterozoic from a chemically active composition of carbon dioxide to a neutral composition should, of course, have affected the organization of terrestrial life. Apparently, the appearance in the Proterozoic of fundamentally new forms of unicellular, eukaryotic organisms and algae containing a nucleus and other clearly isolated organs should be associated with this. This shows that a second great tectono-geochemical boundary of the Precambrian, also known as the GOE boundary, or the Great Oxidation Event, which occurred about 2.4 billion years ago, when the oxygen concentration of the Earth's atmosphere increased significantly as a result of the onset of oxygenic photosynthesis, radically changed the entire geodynamics of the Earth and predetermined the emergence of more perfect eukaryotic forms. This event, along with the subsequent development of biomineralization and the growth of biological productivity, led to significant changes in the nature of sedimatogenesis. Some scientists draw attention to the fact that at the peak of stromatolites in the early Proterozoic, specifically 2.3 to 2.6 billion years ago, there was a significant increase in the proportion of heavy carbon isotopes in the carbonates. They believe that the main driver of this increase may be due to the unique expansion of cyanobacterial ecosystems recorded in the stromatolite record. However, the cause of such a blossoming of bioproductivity, which was noticed precisely during the period of massive deposition of iron ore formations, when the partial pressure of oxygen should have been minimal throughout the history of the development of life on Earth, is being investigated. This is probably due to the fact that cyanobacteria can live and grow remarkably well in a totally oxygen-free environment. But in the lower Proterozoic, in parallel with the removal of iron oxides from the rift zones, there was also an abundant production of methane. At the same time, despite the rather low pressure of carbon dioxide in the lower Proterozoic atmosphere, its outgassing from the mantle was then about 3 times higher than today. It follows, therefore, that during the deposition of the lower Proterozoic iron ore formations, the rate of abiogenic methane production was also at least 3 times higher than today, and according to scientists' estimates, it would have reached 10 million tons per year. In the oxygen-free environment of the lower Proterozoic, this methane was not oxidized, but was almost entirely consumed by the nutrition of methane-consuming bacteria, which probably predetermined the flourishing of stromatolites. On the other hand, due to the isotopic fractionation of carbon in the exchange reactions of carbon dioxide with methane, there is always enrichment of methane in the light carbon isotope, and the remaining carbon dioxide, which is then transformed into carbonates, becomes, on the contrary, isotopically heavier. This is the cause of the decrease in the proportion of organic carbon isotopes during the deposition of the upper Archean and lower Proterozoic iron ore formations. Later, after the end of the iron ore accumulation era and the subsequent increase in the partial pressure of oxygen in the atmosphere, most of the methane began to be oxidized by it, and the light methane carbon began to return to its carbonate reservoir. As a result, the role of the carbon dioxide exchange reaction with methane decreased significantly in the mid-Proterozoic, leading to the disappearance of the positive carbon isotope anomaly. The total biomass of oxygen-generating phytoplankton in the ocean is determined by the amount of phosphorus compounds dissolved in its waters, but its concentration in ocean waters has always remained in equilibrium with the basalts of the oceanic crust and is close to the present. It follows that the mass of oceanic phytoplankton has increased over time, approximately in proportion to the increase in the mass of water in the ocean. In the absence of the process of oxygen association in rocks, its accumulation in the Earth's atmosphere would follow the same pattern. Considering the evolution of life in the history of the Earth, it is important to look at a circumstance that was not previously considered. It is the presence in the Precambrian mantle of free iron. Along with the mantle material, this iron entered the rift zones of the mid-ocean ridges, where it was oxidized upon contact with water into a soluble, divalent hydroxide, probably in the form of bicarbonate, which was transported further into the ocean. But as is well known, divalent iron hydroxide is an active oxygen scavenger. This suggests that most of the oxygen produced by Precambrian phytoplankton was then rapidly expanded in the oxidation of divalent iron hydroxide to the trivalent state, for example, as goethite. This should explain not only the formation of the most powerful Precambrian iron ore deposits, but also the very low partial pressure of oxygen in the Precambrian atmosphere. During the process of chemical density differentiation, iron, accompanied by its oxides, gradually moved from the mantle to the Earth's core, but it did not completely disappear from the mantle until the turn of the Proterozoic and Phanerozoic. After the complete transition of metallic iron from the mantle to the core about 600 million years ago, the main consumer of oxygen on Earth disappeared, and this vital gas began to accumulate rapidly in the atmosphere. Moreover, the process of decomposition of organic residues after the death of the organisms themselves is a powerful mechanism for oxygen uptake. This shows that only the burial of organic carbon in sediments in the form of hydrocarbons or chars leads to the accumulation of oxygen in the atmosphere. In the Proterozoic and Lower Paleozoic, terrestrial vegetation did not yet exist, and thus there was no accumulation of charcoal until the middle of the Paleozoic. But the preservation of hydrocarbons in oceanic sediments, oil shales, and black shales already occurred in the Precambrian. Moreover, the power of this process in the Proterozoic is expected to be even greater than in the Phanerozoic, since at that time, a reducing environment prevailed in the oceans, and the organic remains of phytoplankton were preserved in the sediments without oxidation. Nevertheless, to this day, the ancient oil and gas accumulation basins have hardly survived, but have been destroyed by later tectonic processes. Therefore, their quantitative distribution in present-day geologic sections cannot be used as a criterion to assess the intensity of these processes in ancient times, although graphitic rocks and black shales were quite widespread in the Precambrian. It follows from the above that the rate of oxygen generation in the Proterozoic was quite commensurate with that of today. But in the Precambrian, almost all the oxygen released was absorbed by the iron oxidation process due to the vital activity of phytoplankton. As a result, the partial pressure of atmospheric oxygen, which remained low until nearly the end of the Proterozoic, began to increase rapidly in the Vendian, i.e., about 650 million years ago. Biological evolution literally responded to this with an explosion of new life forms on Earth. the appearance of multicellular algae, and above all, the emergence of metazoans, which are the multicellular representatives of the animal kingdom, whose metabolism was already based on the consumption of oxygen from the external environment. In addition, skeletal organisms, and almost all types of organisms known today, appeared at the beginning of the Cambrian. Thus, the third geological and biological milestone of the Proterozoic to Phanerozoic transition was clearly reflected in the geological history of the Earth and radically changed the ecological situation at its surface. The Earth's atmosphere now changed from a reducing to an oxidizing neutral atmosphere. In this new situation, life forms whose metabolism was built on oxidation reactions of organic substances synthesized by the plant kingdom proved to be the most efficient. With the beginning of the Phanerozoic, the situation changed radically. Oxygen appeared in the atmosphere. This is the main factor that predetermined the prosperity of complex life forms on Earth. Reorganizations of biota also took place in later geological epochs, but all of them already had the character of differentiation and evolutionary development of organisms within the large taxa formed at the beginning of the Phanerozoic. At the same time, in addition to the main factor on the evolution of life in the Phanerozoic, which is the progressive increase of the atmospheric pressure of oxygen, other factors caused evolutionary changes in the forms of life, such as the continental drift, climatic changes, transgressions and regressions of the sea. All these factors altered the established ecological niches of biological communities and intensified their competition for survival. During the Phanerozoic, two major global transgressions occurred. The first developed from the Ordovician to the Devonian, i.e. from about 500 to 350 million years ago. Its amplitude is about 250 meters or 820 feet. The second closest global transgression took place in the Cretaceous and reached an amplitude of about 400 meters or 1,300 feet. In addition, the conservation of water in the continental ice caps during the ice ages resulted in global ocean regressions with a decrease in ocean level of about 130 meters or 425 feet. Ocean-to-land transgressions and their reverse regressions associated with eustatic fluctuations in ocean level must have had a significant impact on global variations in Earth's climate in the geologic past. Because the heat capacity of water is far greater than that of continental rocks in the atmosphere, any significant increase in sea surface due to a decrease in land area attenuates seasonal and latitudinal climate changes. By inundating up to 40% or more of the continental surface, the softening effect of transgressions on global climate variations in temperature and high latitudes must have been quite large, especially when one considers that the expansion of the epicontinental seas created new sea corridors through which heat could be exchanged between low and high latitudes. During periods of regression, as the sea retreated, the overall continentality of the Earth's climate increased. Seasonal temperature contrasts also increased, and there was cooling in the temperature and high latitudes. The spatial arrangement of the continents and oceans also significantly affects the latitudinal zonation of climate. Large areas of land, located in the polar regions, as the lithospheric plates move as a whole, begin to be progressively covered by mountain glaciers, which thus play the role of a global refrigerator. Thus, the most pronounced latitudinal zonation on Earth is observed when there are large land masses in the polar regions. A decrease in land area in the polar regions, for example, as a result of transgression, and even more so, the complete absence of large continental fragments in these regions, generally led to a significant smoothing of the latitudinal zonation and a climatic warming of the Earth's climate, as observed, for example, during the existence of Pangaea. In addition, changes in the relative position of the land masses have altered the nature of the circulation of ocean waters, which has also strongly influenced the formation of the Earth's climate. It is known that the modern glaciation in Antarctica began only after Australia broke away from it and moved northward, and the Drake Passage opened between Cape Horn at the southernmost tip of the South American continent and Antarctica. After that, a southern, circumcontinental current formed around Antarctica, completely cutting off this continent, parallel to the warm counter-exchange currents of the three oceans surrounding it. This climate isolation system for Antarctica is still in place today. Following the geohistorical interpretation of global climate change processes on Earth, we will attempt to consider the nature of the major ecological boundaries of the Phanerozoic, i.e., the processes that took place during the last 550 to 600 million years of life's development on our planet. Thus, a gradual increase in atmospheric oxygen pressure allowed, about 400 million years ago, a highly organized life capable of living on land. This event is a unique phenomenon associated with a radical restructuring of the metabolism of organisms and the appearance in the animal kingdom of forms with lungs, an organ ideally suited to gas exchange in the air. Considering that the Sun and other cosmic factors have almost no effect on the development of the Earth, we can confidently state that purely terrestrial factors played a leading role in the development of life. Of course, our planet is one of many cosmic bodies, but the emergence of life in the form we know it is a unique, specifically terrestrial phenomenon. The main causes of ecological evolution in the Phanerozoic, as in previous eras, were also due to global tectonic processes. This hypothesis is well illustrated by the example of the development of life in the ocean. Indeed, the change in the spatial arrangement, size and shape of the continents and oceans in the Phanerozoic history of the Earth had a significant impact on the strength and structure of ocean currents, and consequently, on the distribution of biological productivity, i.e., on the formation of the ecological systems best suited to certain natural conditions. To illustrate the dependence of the development of life on lithospheric plate tectonics, it is useful to consider the influence exerted on the distribution of species of marine organisms by the location of continents and oceans, as well as by the climatic zonation of the Earth. It is known that the vast majority, almost 90%, of all marine animal species live on continental shelves or in shallow waters near underwater hills and islands at depths less than 200 meters or 650 feet. Therefore, it can be considered that in the Phanerozoic, the main development of the marine fauna occurred at shallow depths. At the same time, the shallow marine fauna is now found in the tropics, where it is saturated with a large number of highly specialized species. The diversity and abundance of marine fauna decreases with increasing latitude, especially in oligotrophic oceanic areas. However, in circumpolar waters, there has been a significant increase in ocean bioproductivity again, due to the increase in dissolved oxygen concentration in these waters, while the lowest ocean productivity has been observed at mid-subtropical latitudes. The degree of diversity of the current shallow marine fauna correlates well with changes in the sustainability of food stocks, which depend on the seasonality of climate. In addition to this most important latitudinal factor, there are also longitudinal components that also determine the overall diversity of the present-day marine fauna. In particular, at the same latitude, greater faunal diversity is observed where there is stability of food resources. Thus, in each latitudinal zone, the greatest diversity of marine fauna is observed near the coasts and island archipelagos. Of particular note are the upwelling zones, where deep waters rich in phosphorus and organic compounds rise along the continental slope to the surface, providing abundant food for shallow water organisms. Upwelling generally occurs on the eastern shores of the oceans in their tropical zones. In these areas, special life environments emerge, flourishing beautifully among the relatively deserted waters of adjacent oligotrophic water zones, including the Peruvian and West African upwelling zones in the Pacific and Atlantic Oceans. Naturally, deep ocean basins formed as a result of rifting, the extensional movement of the lithosphere, become a significant barrier to the spread of shallow water fauna. Volcanic island arcs that occur above areas of oceanic lithospheric subsistence into the mantle and interplate chains of volcanic islands often provide good pathways for the spread of marine fauna, especially when these volcanic island chains are located below latitude or are located, such as the islands of Polynesia and Micronesia, within the same climate zone. Migration of larval forms of animals may be another mechanism for dispersal of shallow water fauna. Nevertheless, due to the current, rather fragmented position of each of the major continents, the shallow marine fauna inhabiting their shelves currently occurs in 30 regions and is characterized by a relatively small percentage of species common to all of these regions. Estimates show that the shallow water marine fauna now has an order of magnitude more species than would be observed if there were only one faunal shelf region on Earth, even with greater species diversity. The same patterns can be traced with the distribution of some deep-sea fauna species. For example, in the biological communities of hot springs, also called black smokers in the Pacific Ocean, large tube worms, vestimentifers, and bivalve mollusks dominate, whereas in the Atlantic Ocean, the same hydrothermal springs are entirely occupied by small shrimp that have adapted by feeding on sulfur bacteria. From these faunal distribution patterns, and taking into account data on continental drift and information on eustatic changes in global ocean level, as well as the climatic consequences of these phenomena, one can attempt to explain the nature of the change in the number of shallow water faunal taxa in the Phanerozoic, e.g., the mass extinction of many animal groups at the Paleozoic Mesozoic boundary. Indeed, the distinct lower Paleozoic position of most landmasses and their predominant location in tropical and temperate latitudes, as well as the presence of shelf areas for each of them, led to a significant increase in the number of families in the Ordovician shallow water fauna. This increased number of families was maintained throughout the evolution of the marine fauna throughout most of the Paleozoic. At the Permian-Triassic boundary, when nearly all continental fragments were united into a single supercontinent, Pangaea, the Earth's climate warmed, and the number of biological regions and ecological niches on the Pangaean shelf was significantly reduced. In addition, Permo-Triassic regression led to a sharp reduction in the area of shallow seas. Under such conditions, at the boundary between the Permian and Triassic, only those representatives of the shallow water fauna that could find food in the lower layers survived. In other words, the faunal families that survived at the turn of the Paleozoic and Mesozoic should have been ecologically similar to those that survive today under unstable environmental conditions, whereas the populations that developed in the Paleozoic under stable conditions similar to the present-day tropics after the formation of Pangaea proved to be less adapted and doomed to extinction. Therefore, it can be assumed that the rapid extinction of many marine fauna species at the turn of the Paleozoic and Mesozoic was due to a decrease in the number of ecological niches surrounding the then-formed supercontinent, and a decrease in the bioproductivity potential surrounding this single continent of continental seas. In contrast, the separation of the continents that began in the early Mesozoic, accompanied by the transgression of the seas onto the land, and the significant global warming of the Earth's climate, led to a progressive increase in the number of marine basins isolated from the shelf. During the Cenozoic, the diversity of the animal world increased dramatically, particularly due to the appearance of new climatic regions on Earth, as well as the fragmentation of the continents into multiple distinct regions. This evolution has thus led to a significant increase in biodiversity. Of course, such a general approach to the problem of the evolution of life requires significant development in detail. For example, the Cretaceous transgression led to the flourishing of carbonate fauna and microflora on plateaus and in epicontinental seas, especially the Coccolithophora microflora, which formed unique chalk strata. However, the same transgression also caused crisis phenomena in the life of deep-sea coral atoll biocenoses. It is felt that in the mid-Cretaceous a powerful mechanism existed, leading on the one hand to a strong weakening of oceanic sedimentation, and on the other hand to an increased transfer of calcium carbonate in the waters of the open ocean to the shallow seas of the flooded areas of the former land. During the Cretaceous period, the location of the continents on the Earth's surface was completely different from that of today, and most of the shallow, epicontinental seas were then located in arid areas with a clear predominance of evaporation over precipitation. Therefore, these seas served as natural pumps, pumping water from the oceans. The water entering the epicontinental seas partially evaporated, and the concentrations of salts, calcium carbonate, and phosphorus dissolved in it increased significantly. Since the epicontinental seas at that time were mostly open, the increase in salt concentration was apparently not significant. Nevertheless, good warming and aeration of large but shallow sea basins with increased concentration of calcium carbonate and phosphorus compounds led to the intensive development of life, especially phytoplankton, including coccolithophorids and foraminifera, and the shallow waters corals, mollusks, other skeletal animals, as well as powerful calcareous coarse coral strata that formed in the mid-Cretaceous. Marginal seas are generally natural basins in which avalanche sedimentation develops and river runoff discharges. Consequently, the carbonate material transported by rivers from the continents at this time was mostly deposited precisely in these seas, hardly reaching the waters of the open ocean. As a result, the waters of the world ocean in the mid-Cretaceous were found to be significantly depleted of calcium carbonate and probably phosphorus compounds. A sharp reduction in the supply of calcium carbonate and phosphorus to the biohermal structures of deep-sea atolls that occurred during the Aptian-Cenomanian period led to the suppression and degradation of reef communities that built their calcareous skeletons and frameworks from calcium carbonate. Under conditions of severe carbonate scarcity, corals, rudists, and other skeletal organisms could no longer create strong calcareous structures capable of withstanding the erosive activity of ocean waves, especially during stormy weather. In such a situation, the reef structures of oceanic islands, such as the Aptian, Cenomanian atolls, and rudist beds, no longer had time to build up and compensate by their growth for the progressive subsidence of their volcanic bases below ocean level. The erosion of the ancient reefs eventually completely destroyed the shallow fauna that lived there, transforming the ancient coral atolls and rudist banks into flat-topped seamounts called gyats. Continental drift has also had a significant impact on terrestrial fauna. For example, it is well known that the Mesozoic, along with the Upper Permian of the Paleozoic, was the age of reptiles, while the Cenozoic was the age of mammals. Over 200 million years of development in the Permo-Mesozoic era, only 20 orders of reptiles appeared, while after the Cenozoic, about 30 orders of mammals appeared. The striking difference can be explained by comparing the developmental conditions of reptiles and mammals. It should be noted that the initial period of rapid development of terrestrial reptiles coincides with the formation of two supercontinents, Laurasia and Gondwanaland, a single Pangaea with a period of oceanic regression and with a relatively mild global climate that was established at the end of the Permian, after the shift of present-day Antarctica from the southern polar region to temperate latitudes. In the Triassic and Jurassic, at the beginning of the disintegration of Pangaea, more or less stable ecological links still existed between its fragments. Therefore, during the long period of reptile development on Earth, there was either a single ecological region, or there were a very small number of semi-isolated regions. It is clear that under such conditions a wide variety of reptiles could not have appeared. It was not until the Cretaceous, when the separation of several truly well-isolated continental fragments began, that about half of the total number of orders in the reptile class was formed. The development of 8 to 10 terrestrial ecological regions essentially isolated from each other in the early Cenozoic, represented the main condition for the generic diversity of the mammalian class. It should be noted that the late Cenozoic association of several continental fragments and the reduction of the number of ecological regions to 4 led to the extinction of 13 orders of terrestrial mammals. Mammals that developed prior to the association of different continents under isolated conditions proved, as a rule, less adapted and became extinct. A more general conclusion, based on an analysis of the upper Mesozoic and Cenozoic evolution of the global ocean floor, can only be sketched at this point. All the major boundaries of geological history, and consequently, the division of geochronological history with a scale into eras, periods, and epochs, are largely due to events such as collisions and splits of continents in the process of global movement of the lithospheric plate set. The examples show that the evolution of plant and animal life forms on the continents was apparently also largely determined by continental drift and changing climatic conditions on Earth. This should have been particularly evident during the unification of previously isolated continents, or conversely, during the splits of large continents and the separation of their fragments. The alternation of epochs of consolidation and fragmentation of continents with the formation of common and intercontinental oceans was of course accompanied by the emergence of new and the closure of old ecological niches, i.e. radical changes in the ecological conditions for the existence of life on Earth. Therefore, such rearrangements could probably be one of the main reasons for speciation and extinction of individual life forms, as well as for their conservation. Endemic life forms in Australia and South America can serve as a striking example. Of course, all these events influence the paleoclimate and the whole evolution of the ecological system of our planet in the geological past, which was reflected in the compilation of the geochronological scale and its division into eras, periods, and eventually epochs. Naturally, in the geohistorical analysis of the problem of the evolution of the flora in the geological past, it is also necessary to adopt a mobilist approach and to take into account the ecological balance in each of the zones that were separated and united in the process of drift. Fluctuations in the global climate and the quaternary, with periodic changes in ice and interglacial periods, also influence the development of humanity and determine the times of migration of peoples and the timing of the formation of the racial composition of human beings. For example, the colonization of America through the Bering Strait most likely occurred along a dry route during the lowering of the ocean level caused by the last worm glaciation, which occurred in the northern hemisphere about 150,000 to 112,000 years ago. This glaciation reached its maximum size about 20,000 years ago, but about the same time, it is assumed that the New World was populated by humans. For more than 3.5 billion years, the Earth's biosphere has evolved in close correlation with the geological dynamics of our planet. Thus, in order to understand this evolution, it is essential to carefully study the biospheres of the past, taking into account past geological conditions, tectonic and geochemical boundaries, climate evolution, continental drift, the appearance and disappearance of oceans, etc. These elements allow a comprehensive analysis of the interactions between the biosphere and the historical development of our planet. geological processes have had a direct influence on the evolution of life on Earth. However, there is also a reverse influence, where life has affected some geological processes. Organic life has played a key role in the formation of certain types of rocks, such as carbonates, phosphorites, coal formations, oil deposits, gases, and pelagic sediments. Similarly, life has also played an important role in the weathering processes of rocks and in the processes of the orogenic cycle. In addition, life helped maintain the composition of the Earth's atmosphere, which played a key role in shaping the Earth's climate during the Phanerozoic. The climatic cooling that began in the Cenozoic, caused by the uptake of atmosphere nitrogen by soil bacteria, will continue. Therefore, it is difficult to expect significant climate warming in the next 100 to 200 million years. The current warming of the climate, i.e. well before the Industrial Revolution, and associated with fluctuations in the magnetic activity of the Sun. This in particular is evidenced by paleotemperature measurements over the last 3,000 years from the remains of planktonic foraminifera in the Sargasso Sea, which clearly show that the current local increase in average temperatures is developing in the context of a general cooling of the climate. Indeed, about 100 million years ago, there were no ice caps on Earth, and average temperatures reached nearly 17 degrees Celsius, or 62 degrees Fahrenheit, whereas today they have dropped to 15 degrees Celsius, or 59 degrees Fahrenheit. Following such an insignificant cooling, a new ice age began, resulting in a mid-Cenozoic ice cover over Antarctica, followed by periodic ice ages on the continents of North America, Europe, and Asia in the Quaternary. If the experts' assumptions about the gradual elimination of nitrogen from the Earth's atmosphere and its burial in the Earth's crust are correct, and the organic nitrogen content of precipitation that we accept corresponds to reality, then despite an increase in solar activity, a slow cooling of the climate will continue in the future until a new equilibrium state of cool climate is reached. Nevertheless, this new climate level, determined by the metabolism of nitrogen-destroying microorganisms, may not be very favorable for the flourishing of complex life forms on Earth. It follows that the new ice age, when it occurs in the Northern Hemisphere, will be the most severe. According to estimates of scientists, after 200 million years, the average temperatures on Earth will fall slightly below 12 degrees Celsius or 54 degrees Fahrenheit. At the same time, the level of the world ocean will drop about 200 meters or 650 feet. In this situation, the conditions for the development of highly organized life will remain quite acceptable in the low and middle latitudes. Only after about 400 million years will the average surface temperature of the Earth drop to about 10 degrees Celsius or 50 degrees Fahrenheit, and the ocean level drop more than 500 meters or 1,640 feet from its present position. In this case, all the northern and southern continents, even at modern latitudes, will be covered by glaciers, and the high parts of the continents at the equator will also be covered by ice. But the cold wave will not last forever. In the interval of about 200 to 300 million years, an equilibrium should occur between a decrease in temperature due to the bacterial removal of nitrogen from the atmosphere and its increase due to an increase in the brightness of the sun. However, Even this state of equilibrium in about 600 million years should be strongly disturbed by the outgassing of abiogenic oxygen released during the formation of nuclear material in the mantle. After this time, free oxygen will begin to be generated in the mantle at a rate of about 21 billion tons per year. If all this oxygen were released into the atmosphere, its partial pressure would increase at a rate of about 4 atmospheres every million years. In fact, the rate of oxygen outgassing will be much lower, but it could still reach a rate of about 0.02 atmospheres per million years. This means that after 200 million years from the start of oxygen degassing from the mantle, the partial pressure of this gas will reach nearly 4 atmospheres, while the average temperature of the Earth will rise to nearly 76 degrees Celsius or 169 degrees Fahrenheit due to the greenhouse effect. Therefore, in a billion years in the future, the oxygen pressure will exceed 14 atmospheres and surface temperatures will rise to 110 degrees Celsius or 230 degrees Fahrenheit. Under such conditions, all terrestrial life will literally burn up in such an atmosphere soon after the outgassing of endogenous oxygen begins. Only in the oceans, due to the low solubility of oxygen in water, will complex life forms still be able to exist for some time, until they also disappear from these warm waters. Even the most primitive thermophilic prokaryotes will not be able to survive when the oceans boil over about 1.5 billion years later and temperatures reach about 550 degrees Celsius or 1,000 degrees Fahrenheit, causing an irreversible greenhouse effect. Most likely, the total duration of the existence of life will be about 5 billion years, divided between 4 billion years in the past and 1 billion years in the future. For the development of highly organized life, nature has given even less time in the oceans, a maximum of 1.4 billion years, divided between 600 million years in the past and 800 million years in the future. And on land, no more than 1 billion years, divided between 400 million years in the past and 600 million years in the future.